Picture this. You're a detective trying to solve a complex case. You collect evidence to support your theory, but you need to be sure it's not just a coincidence. This is where the p-value steps in. They're like a truth detector for scientists. A p-value is a number between 0 and 1. It tells you the probability that your research findings are merely due to chance. In essence, the lower the p-value, the stronger the evidence against chance. Typically, scientists set a threshold, often 0.05, as the cutoff. If your p-value falls below this mark, you can confidently say that your findings are statistically significant. Let's turn to an example. Imagine you're testing a new drug's effectiveness. If your p-value is 0.03, meaning below 0.05, it suggests that there's only a 3% chance your results are random. That's promising. But if your p-value is 0.2, above 0.05, it indicates a 20% chance your results occurred by chance. You need more evidence to draw meaningful conclusions. Now you may be wondering, who even cares? Why do we even need a p-value? What is its importance in research? Well, you see, p-values guide scientists by helping them separate true discoveries from mere flukes. Think of them as the sentinels of scientific integrity, ensuring that our understanding of the world is based on the most dependable evidence available. Now diving deeper into the world of p-values, there's a controversial practice that sometimes skews these truth detectors. Can you guess what it is? It's called p-hacking. So what exactly is p-hacking? P-hacking is a form of bias that arises when researchers manipulate data or statistical methods until results that weren't originally significant appear to be so. Imagine you're a detective working on a high-profile case in the city. You've got a room full of evidence, and you need to figure out who the culprit is. Now, you have a theory about the main suspect, Ryan. This is how p-hacking works in 4 steps based on this scenario. At first glance, none of the evidence directly points to Ryan, but you're convinced he's involved. Instead of following where the strongest evidence leads, you start piecing together any tiny clues that might implicate Ryan. You take his fingerprints and try to match them to every single item in the room, hoping for a hit. You examine his alibis closely from various perspectives, searching for inconsistencies. After hours of looking, you find a faint fingerprint of Ryan on a random item. Aha! Though that's not strong enough evidence to consider someone guilty, since it's below the commonly accepted p-value of 0.05, but you're excited to have found something. You don't tell your chief about all the items Ryan's fingerprints weren't on, or the alibis that checked out. You only present the one piece of evidence you found, making your case seem stronger than it really is. Based on this one shaky piece of evidence, you arrest Ryan. But in reality, the print could have been from an unrelated visit. By focusing solely on trying to prove Ryan's guilt, you might have missed vital evidence pointing to the real culprit. In the world of research, p-hacking is similar. It's like trying to force evidence to fit a theory instead of letting the evidence guide the conclusion. And just as in detective work, this can lead to incorrect conclusions, leaving the real culprit or truth undiscovered. Let's now dive into the real-world examples of p-value hacking, where the integrity of scientific research was compromised. In this segment, we focus on one of the most notorious cases, Diederik Stapel. Diederik Stapel, former dean of the Social and Behavioral Sciences faculty at Tilburg University, was exposed for a decade of fraudulent work. Stapel had a crafty way of subtly changing small data details to manipulate results, eventually escalating to full data fabrications. His scientific misconduct was so cleverly executed that it went undetected for many years. However, in 2011, an investigation found that Staples fabricated data for over 55 papers and 10 PhD theses written by students he supervised. The fallout was significant. Staples' fraudulent research led to over 50 retractions, a voluntary renouncement of his PhD, and a formal apology to the scientific community. His actions even led to criminal proceedings against him. In a settlement with Dutch prosecutors, Stapel agreed to perform 120 hours of community service. The case of Diederik Stapel serves as a harsh reminder that p-value hacking is a slippery slope. It underscores the importance of scientific integrity and the need to resist the temptation to manipulate results for the sake of publication or recognition. As we reflect on Stapel's actions, it's clear that maintaining the credibility of science is very important. Now you're probably wondering, how can we detect p-hacking? Well, here are some red flags to look out for. Number 1, the source of information. Is it reputable? Reputable sources include peer-reviewed journals. Peer-reviewed means the article has been looked over by peers, often other researchers, to make sure the study is good quality and is original. If a scientific study doesn't state this, then you should approach the results with caution. Number 2, over-sensationalized results. These are results that seem almost too good to be true, and results which go completely against extensive and existing findings. It's important to remember that nothing is ever all positive or all negative. Number 3, a lack of limitations. You should look for whether the limitations of a finding are included in the scientific study. Ask yourself, are non-significant results talked about, or is it just the significant ones? Are all of the study steps included, or are you left with questions on how researchers got a certain result? Lastly, is the experiment and study repeated by other researchers? As much as readers like us should be wary of findings, it is the job of researchers to ensure that they are being truthful with their practice. And although p-hacking is challenging to detect, raising awareness of this issue can be a good step towards combating lousy science. So, playing detective can be left at the hands of those making new discoveries in an ethical way.